Calorimetry is the measurement of heat flow, and heat, in science, we define as energy in transit from a hotter to a colder object. If we have a vat of boiling water, in science we don't say, wow, that water has a lot of heat. We would say, that water has a lot of internal energy. Only when you stick your hand in it do we scientists say, well, there is some amount of heat that is traveling from the water into this person's hand. Heat in science has a very specific meaning. It's energy in transit from something warmer to something colder. The device that we use in calorimetry is called a calorimeter. The heat capacity of an object is the amount of heat needed to raise the object's temperature 1 Kelvin, or 1 degree Celsius, because a step on the Kelvin scale and a step on the Celsius scale are the same step. The molar heat capacity, as the name would suggest, is the amount of heat needed to raise the temperature of 1 mole of a substance, 1 Kelvin. The specific heat capacity, or sometimes it's just shortened to specific heat, is the amount of heat needed to raise the temperature of 1 gram of a substance, 1 Kelvin. For example, for water, if the specific heat is 1 calorie per gram Kelvin, then the molar heat capacity would be 18 calories per mole Kelvin. In other words, the molar heat capacity is the molar mass of water, which is 18, multiplied by the specific heat. If you just use the units and make sure that you cancel them whenever you're doing a calculation, most of the time you're going to have no problem. We calculate the heat a substance loses or gains using two equations. Here's one of them. Q is equal to mc sub p delta T. The other one is Q is equal to plus or minus m c sub f or c sub v, depending on what you're doing. And we're going to go ahead and explain how to use these equations. The one on the left is used whenever we're within a given state of matter. We're at some temperature for a liquid and we're heating it up to warm the liquid. The equation on the right is when we're changing states of matter. So when something is melting or freezing or boiling, we would need to use the equation on the right. In other words, on the left, within a state of matter, there is going to be a temperature change. Hopefully you've learned in previous studies of chemistry that whenever we have a transition in a state of matter, for example, when water is boiling, it doesn't change temperature while it's boiling. These variables, Q is the heat, usually in joules, M is the amount of substance, and I came up with this notation M with a line under it to generalize that amount of substance. Maybe it's given in grams, maybe it's given in moles. That way the same equation applies for either case. C sub P is the heat capacity. Now it could be the molar heat capacity, sometimes that's given, or it could be a specific heat capacity, but in any case, the heat capacity of the solid phase is different from that of the liquid phase and is different from that of the gaseous phase. So we need to pay attention to what state of matter we're in and choose the appropriate heat capacity. Delta T is obviously the temperature change, and again, it doesn't matter if we're in Kelvin or Celsius, because we're taking a temperature difference, and the difference between two temperatures in kelvins and the difference between two temperatures in Celsius is exactly the same. And then C sub F or C sub V is the heat of fusion or the heat of vaporization. C sub F obviously for the heat of fusion, C sub V for the heat of vaporization. These are the constants that you would use if you are undergoing a state of matter transition from the solid to the liquid, or liquid to the solid, or if we're going from liquid to gas or gas to liquid. Here is a typical heating curve. Heat is plotted on the horizontal axis and temperature is plotted on the vertical axis. Down here in the lower left, that indicates the solid phase. This stretch in the middle is the liquid phase. So the horizontal portion between those is when we are transitioning between solid and liquid. In the upper right, we have the gas phase. So that horizontal transition between liquid and gas is when we are, for example, going to be boiling. As we move to the right up this curve, we're adding heat. As we move to the left, we're taking heat away. We would use several constants in solving a problem, and the constants that we would use would depend on where we are on this diagram. If we're on a sloped portion, we're going to use a heat capacity of some sort. The heat capacity of the solid, or the heat capacity of the liquid, or the heat capacity of the gas. If we're on a horizontal region, if we're in the solid-liquid horizontal portion, we're going to use the constant C sub F, the heat of fusion. And if we're on the liquid-gas horizontal portion, we're going to use the heat of vaporization. I don't know if this will help you or not, but that equation is to be used when we're on any of these sloped portions of the graph. This equation needs to be used when we're on a horizontal portion of the graph. We'll show you examples of these and do some actual calculations in future lessons. How do the magnitudes of the heat of vaporization and the heat of fusion compare? Well, the answer is that the heat of vaporization is typically quite a bit larger, and there's a good reason for that. In vaporizing something, that is, in making it boil, the intermolecular forces between the particles must be completely overcome for the particles to enter the gaseous phase. When we're using the heat of fusion, we're simply melting something, and the particles in the solid phase are very close together. Then, when they've melted and the substance is in the liquid phase, again, the particles are still very close together. Now, they have more kinetic energy than when they're in the solid phase, but they still are very close together. We have to increase the kinetic energy enough to allow the particles to slide relative to each other, but the intermolecular forces are still in effect. As an example, for water, we can see that the heat of vaporization is roughly 7 times larger than the heat of fusion. Here's our summary to this lesson, Introduction to Heating Curves. We have a heating curve here. We're adding heat if we move to the right. We're taking heat away as we move to the left. If we're on a slanted portion of the curve, we need to use the delta T form of the equation, which I've circled in blue in the lower right, and we need to use one of the constants, namely the heat capacity that is specific to that state of matter. If we're on a horizontal region, then the substance is changing phase. It's going from a liquid to a solid, or a solid to a liquid, or a liquid to a gas, or a gas to a liquid, and there is no temperature change when that's happening. So we have to use a different form of the equation. In the lower right, I've boxed it in green, and again we need to use a constant that is specific to what we're doing, whether we need to use C sub F, the heat of fusion, for solid-liquid transitions, or the heat of vaporization for liquid-gas transitions.